Hey everyone, today I want to talk about DFA NFA equivalence, and in particular, I want to talk about the process of translating an NFA into an equivalent DFA. Now, what exactly does it mean for an NFA and a DFA to be equivalent? Well, a DFA is equivalent to a particular NFA if it recognizes the same language as that NFA. So that's what we're going to try to do today, is given any NFA, we want a process that's going to turn that NFA into a DFA that recognizes the same language. Now, before I get into that, we're going to have to talk about a concept that I haven't gone over yet, and that is the concept of the epsilon closure. Now, what exactly is the epsilon closure? Well, in a nutshell, the epsilon closure of a state or set of states is the set of states in the NFA that are reachable by taking 0 or more epsilon transitions from those states. So in order to make that a little bit more clear, let's go ahead and do an example. So the epsilon closure is denoted by this capital E, and we're going to put the set of states we want to take the epsilon closure of in curly brackets. So for this example, just to keep it simple, let's just take the epsilon closure of the state 1. So all we're going to put in these curly brackets are just 1 to represent that we want to take the epsilon closure of the state 1. Great. So recall the definition that I just gave. We want to find the set of states in the NFA that are reachable from the state 1 by taking 0 or more epsilon transitions. And the first thing that you should immediately notice is that the state 1 is going to be in our epsilon closure, right? Because if we are at the state 1, we can reach the state 1 by taking 0 epsilon transitions. So we know that 1 must be in the epsilon closure. And it's actually the case that all of the states in the set that we're taking the epsilon closure of are automatically in the epsilon closure by definition. So in the future, when we take the epsilon closure of a set of states, we just include all of the states in this set automatically. Great. So we know that 1 must be in the epsilon closure. Now, are there any other states in the NFA that are reachable from state 1 using epsilon transitions? Well, yes, there are. We can reach the state 3 by taking this epsilon transition from 1 to 3. Therefore, we know that the state 3 must be in the epsilon closure. Now, what about the state 2? Can we reach state 2 by taking epsilon transitions from state 1? No, we cannot. Therefore, since we've gone through all of the states in the NFA and identified all of the states reachable from 1 by taking 0 or more epsilon transitions, we know that the set containing the state 1 and the state 3 is the epsilon closure of the state 1. Great. Let's do another more complicated example to make sure that we understand the concept. So this time, let's take the epsilon closure of the set of states 1 and 2 this time. Cool. So we need to identify the set of states in the NFA reachable from the state 1 or the state 2 by taking 0 or more epsilon transitions. So recall from the last example that all of the states within the set that we're taking the epsilon closure of are automatically in the epsilon closure. Therefore, the states 1 and 2 are in the epsilon closure. Now, what about the state 3? Can we reach state 3 by taking epsilon transitions from the state 1 or the state 2? Yes, we can. There's an epsilon transition from 1 to 3, therefore 3 is in the epsilon closure. And since we've checked all of the states, we know that the set containing the states 1, 2, and 3 is the epsilon closure of the set containing the states 1 and 2. Great. So that's the concept of the epsilon closure. Now let's actually get into the translation process. Okay, so now to actually do the translation from our NFA into an equivalent DFA, I think what's going to be easiest is if we go through our set of requirements for our DFA and just cross them off one by one. So the first thing that our DFA needs is a finite set of states. So let's call that Q prime. And Q prime represents the set of states in our DFA. Now, we're actually going to set this equal to the power set of Q, where Q is the set of states in our NFA. Now, what is the reason that we're setting our set of states in the DFA equal to the power set of the set of states in the NFA? Well, the reason is because it's going to allow us to model the case where we're in 0 states in the NFA at a particular time, the case where we're in 1 state, and the case where we're in multiple states at a particular time. And the reason why this works will become more evident when I actually draw out the states in the DFA, and I'll explain it in a little bit greater detail when I do that. But for now, let's just calculate the power set of Q and actually draw in our set of states. So the power set of Q is going to contain the empty set, the set containing the state 1, the set containing the state 2, the set containing the state 3, the set containing the states 1 and 2, the set containing the states 1 and 3, the set containing the states 2 and 3, and finally the set containing the states 1, 2, and 3. Great, so this is our power set. Now let's go ahead and draw in all of our states in our DFA, where each state corresponds to one of these subsets in the power set. Let's go ahead and erase this. Great, so now let's draw in our states in our DFA. So we're going to have a state corresponding to the empty set, a state corresponding to the state 1 in the NFA, a state corresponding to the state 2 in the NFA, a state corresponding to the state 3 in the NFA, state corresponding to the states 1 and 2 in the NFA, a state corresponding to the states 1 and 3 in the NFA, a state corresponding to the states 2 and 3 in the NFA, and finally, a state corresponding to the states 1, 2, and 3 in the NFA. And I think it should be a little bit clearer what these states represent based on how I described them, but just to be super explicit about it, let's just go through each of the states and explain what it represents. So let's start in the top left with this empty set state. So this empty set state is representing the case in the NFA where we transition to none of the states. So an example of that occurring would be on the state 3, right? Because on the state 3, if we read in the character B, there are no outgoing transitions from the state 3 on the character B, which means that if we read in a B in our string, we're going to transition to none of the states in the NFA. So in the DFA, the way that that's going to be modeled is transitioning to the empty set state. Next, we have these three states right here that each correspond to exactly one of the states in the NFA. And they do exactly what you think they do. This state containing the set corresponding to the state 1 in the NFA simply represents just being in the state 1 in the NFA and none of the other ones. And then the same thing for this next state here that corresponds to the state 2 in the NFA. It simply represents being in just state 2 and none of the other ones in the NFA. And then the same logic applies for this state over here in the top right. Great. Now, the states on the bottom all correspond to situations in which we're in multiple states at the same time, right? So this bottom left state, which corresponds to the states 1 and 2, represents being in the states 1 and 2 at the same time. And then this next state here that corresponds to the states 1 and 3 represents being in the states 1 and 3 at the same time. And then the same logic applies for the last two states. So that is why we're using the power set of Q as our set of states, because the power set allows us to obtain every single combination of states in the NFA. So it allows us to model being in any combination of states in the NFA at a particular time. So that is the set of states in our DFA. Next, let's talk about the start state. Okay, so how are we going to determine which of the states in the DFA is the start state? Well, in order to do that, we're actually going to use the concept we learned earlier, which was the epsilon closure. So in order to find our new start state in our DFA, which we're going to call Q naught prime, we're actually going to set it equal to the epsilon closure of the start state in our NFA, which is the set containing the state 1, right? Because the state 1 is the start state. So we need to find the epsilon closure of the set containing the state 1, and we actually already did this earlier. The epsilon closure of this set of states is the set containing the state 1 and the state 3, right? Because we can get to 1 by taking 0 epsilon transitions, and we can get to 3 by taking this epsilon transition right here. So the epsilon closure of the set containing the state 1 is the set containing the states 1 and 3. And so we're going to select the state in our DFA that corresponds to this set, the set containing the states 1 and 3, which is this state right here. So we're actually going to set that state as the start state. Now, why exactly are we making this state in particular the start state? Well, if we come over here to our NFA, well, we know that 1 is the start state, right? However, we can also get to the state 3 without consuming any characters, which means that the state 3 also serves sort of as a starting position for processing our string, because we can reach the state 3 without consuming any characters in our string. So really, being in the states 1 and the states 3 correspond to being in the start state. So that's why the state corresponding to being in the state 1 and the state 3 is the start state in our DFA. Next, let's go ahead and talk about our set of accept states. Okay, so figuring out our set of accept states in the DFA is actually going to be pretty easy. All we're going to do is simply look at all of the states in the DFA, and if that state contains an accept state from the NFA, then we're going to make that state an accept state. So let's go ahead and do that. So the empty set state does not contain any of the states from the NFA, so we're not going to make that an accept state. The state containing just the state 1 from the NFA, well, 1 is an accept state. So because our set here contains an accept state from the NFA, we're going to make this state an accept state. Great. Now what about the set corresponding to the state 2? Well, it does not contain an accept state, so we will not make this an accept state. And the same thing for the state 3 here. Now, what about the bottom left state here? Well, an accept state, which is the state 1, is contained within the set here. So we're going to make this state an accept state. Now moving on, this state also has a 1, so we'll make this an accept state. And then this state to the right does not contain 1, so it does not have any accept states from the NFA, so we will not make this an accept state. And finally, this bottom right state here does contain 1, so we will make it an accept state. Now, why exactly are we setting it up this way? Well, the reason is because if we transition to one of these states where 1 is in the set, that means that we are in, let's take this bottom left state, for example, where it corresponds to being in the state 1 and in the state 2 at the same time. Well, if we finish processing our string on that state, that means we're both in state 1 and state 2 at the same time in the NFA. So if we finish processing our string there, that means that one of our possible paths was to end on state 1, which is an accept state. And remember, an NFA accepts a string if there's even one possible path from the start state to an accept state where the string finishes processing on that accept state. So because if we end up in one of these states where ending on 1 is a possibility, we're going to make that an accept state because there is a path that exists to get to an accept state in the NFA. Great. Now let's talk about the alphabet. Okay, so the alphabet is also going to be really simple. So remember in the NFA, well, in this particular NFA, our alphabet is the characters A and B. We could just replace them with like 0 and 1, but it doesn't really matter. So it has the characters A and B, right? But NFAs also have this epsilon character to represent the epsilon transitions. Well, in our DFA, because we don't have any epsilon transitions, our alphabet, which we'll simply call sigma prime, is simply just going to contain the characters A and B, but no epsilon. And the reason for that I just explained, right? Because there's no epsilon transitions in a DFA. And now for the hard part, I think, which is going to be our transition function. Okay, so we're now on to our final part of our translation from this NFA into an equivalent DFA, which is filling out the transition function. Now, this part is probably the hardest part just because there's the most steps to do and it's pretty tedious. And the reason for that is because recall that in the DFA case, every single state in the DFA must contain a transition for every single character in the alphabet. So because we have 2 characters in our alphabet in 8 states, that means we're going to have to fill out 16 different transitions. So it's going to be a little bit tedious, but the process for actually filling out the transitions isn't too bad. So essentially what the process is going to be is, let's say for example, we're on a particular state in the DFA and we want to fill out the transition for character A. So we want to know where do we transition to from that state on character A. Well, let's say for example we're looking at this state right here. So this is the state that corresponds to being in just the state 1 in the NFA. Well, if we want to find where we want to transition to on that state, on the character A, we're simply going to look at the state 1, so that's the state inside of this set here, and we're going to look at, well, what are all of the states in the NFA that are reachable from the state 1 on the character A? And then we're going to find out what that set is. And then once we find out what that set is, we need to do our second step, which is to take the epsilon closure of that set. And then once we take the epsilon closure, the set that we get out of that is the state that we want to transition to in our DFA. So having said that, I think the best way to understand this is to simply do it by example. So let's simply just go through all of the states in the DFA and fill them out, and we'll attempt to learn exactly how to do this just by doing multiple examples of it. So let's start with the state right here in the DFA, which corresponds to just being in the state 1 in the NFA. So we want to identify the set of states in the NFA that are reachable from the state 1 on the character A. Now, notice on the state 1 that there are no outgoing transitions on the character A, which means that we basically transition to none of the states on the character A on state 1. And remember that our state in the DFA that corresponds to that situation of being in none of the states in the NFA is the empty set state. So essentially, the set that we just found was the empty set when we found the set of states reachable from the state 1 on the character A. Now, the second thing we have to do is take the epsilon closure of this set. So if we take the epsilon closure of the empty set, well, that's going to be the set of states reachable from nothing on epsilon transitions. Well, since we're on none of the states, there are no epsilon transitions to even take. So therefore, the epsilon closure of the empty set is simply the empty set. Therefore, on the state corresponding to just being in the state 1 on the NFA, we're going to transition to the empty set state on the character A. So that's how the process works. So let's go ahead and apply that same process for the character B. So again, we want to start on the state 1, and we want to find the set of states in the NFA reachable from 1 on the character B. And while there's one transition from the state 1 to the state 2 on the character B, so that's going to be our set. We're going to have the set containing just the state 2. Next, we need to take the epsilon closure of this set. So remember that in the epsilon closure, all of the states in the set that we're taking the epsilon closure of are automatically in the epsilon closure. So we know 2 must be in the epsilon closure. Now, are there any other states reachable from state 2 using epsilon transitions? No, there are not. So the epsilon closure is simply just the set containing the state 2. Now that we've done both operations, we can say that we're going to transition from state 1 to state 2 in the DFA on the character B. Great, so we've just filled out all of the transitions on state 1, so let's do the same for the rest of the states. So now we're looking at this state here that corresponds to just being in the state 2 in the NFA. So let's start at state 2 in the NFA and figure out what states are reachable on the character A. Well, on the character A, we can take this self loop back to 2, so we know 2 is going to be in our set, or we can take the transition to 3 on A, so 3 is also in our set. Now we need to take the epsilon closure of this set. And well, the epsilon closure needs to contain 2 and 3. And are there any other epsilon transitions from 2 or 3 that go to 1? No, there are not. So this is going to be our epsilon closure. Therefore, on state 2, we're going to transition to the state 2, 3 on the character A. Great, now let's do the character B. On state 2, the only state reachable on character B is state 3. So we're going to take the epsilon closure of the set containing the state 3. And well, there are no outgoing epsilon transitions from the state 3, so the epsilon closure is simply the set containing the state 3. Therefore, on the character B, we transition from state 2 to state 3 in our DFA. All right, let's move on to the next state. The next state represents being in just the state 3 in the NFA. Therefore, let's start at 3 and find the set of states in the NFA reachable on the character A. So from 3, we can take this A transition to 1, and that's it. Therefore, we're going to take the epsilon closure of the set containing the state 1. And we know 1 has to be in this set, and then there's also this epsilon transition from 1 to 3. So 3 is also in the epsilon closure. Okay, now that we found the set, we know that we're going to transition from the state 3 to the state 1, 3 on the character A. Great. Let's go ahead and do the same for character B. So if we start at state 3, there are no outgoing transitions from state 3 on the character B. Therefore, we've obtained the empty set. Now if we take the epsilon closure of the empty set, that's always the empty set. Therefore, on character B and on state 3, we transition to the empty set state. So go ahead and draw an arrow through here. Great. Now let's do the bottom row. So now we're looking at the state at the bottom left, and this state corresponds to the idea of being in the state 1 and the state 2 at the same time in the NFA. So what we're going to do is we're going to start at the states 1 and 2 and look at the set of states in the NFA reachable from 1 or 2 on the character A. So on state 1, there are no states reachable on character A, and on state 2, 2 and 3 are reachable on character A. So we want to take the epsilon closure of the set containing the states 2 and 3. And it looks like there are no epsilon transitions to 1 from 2 or 3, so the epsilon closure will simply just contain 2 and 3. Great. So on the state 1, 2, we transition to the state 2, 3 on the character A. Next, for character B, let's look at the states 1 and 2 and find the set of states in the NFA reachable on character B. So from 1, we can transition to 2, and on 2, we can transition to 3 on the character B. Therefore, we're going to take the epsilon closure of the set containing 2 and 3, which we just did, and that equals the set containing 2 and 3. Therefore, on the character B, we're going to transition from 1, 2 to 2, 3. So we can go ahead and put a little comma here in the character B to represent that this transition is taken on both characters A and B. Great. Let's move on to our start state 1, 3. So this state represents being in states 1 and 3 at the same time in the NFA. So let's start on 1 and 3 and find the set of states reachable on the character A from those two states. So on state 1, we can reach nothing using the character A, and on state 3, we can reach state 1 on the character A. Therefore, we're going to take the epsilon transition of the set containing the state 1, which we've already calculated to be the set containing 1 and 3. Therefore, we're going to have a self loop from 1, 3 back to itself on the character A. Great. Now for the character B, it looks like we can reach state 2, and it looks like that's it. So we're going to take the epsilon closure of the set containing 2, and it looks like that's just going to be the set containing 2. So on the state 1, 3, we're going to transition to the state 2 on the character B. Awesome. Now let's move on to the state 2, 3. So from 2 and 3 on character A, we can reach 2, 3, and 1. So we're going to take the epsilon closure of the set containing all 3 states. And since all 3 states are in this set, well, the epsilon closure needs to contain all 3 states. And that's it. So the epsilon closure is just the set of all of the states. So on 2, 3, we're going to transition to the state 1, 2, 3 on the character A. All right, for character B, if we start on 2 and 3, it looks like we can reach, let's see, we can reach 3, and that's it. So we're going to take the epsilon closure of the set containing 3, which is just going to be the set containing 3. So on the character B, we transition from the state 2, 3 to the state 3. Okay, cool. Now let's move on to the state 1, 2, 3. So if we start in any of these states, what states can we reach on the character A? Well, we can reach nothing on the character, or rather on the state 1. We can reach 2 and 3 on state 2, and we can reach state 1 on state 3. Therefore, we're going to take the epsilon closure of the set containing all 3 states, which we calculated to just be the same set, so the set containing 1, 2, and 3. Therefore, we're going to have a self loop on the state 1, 2, 3 on the character A. Now for character B. So from 1 we can get to 2, from 2 we can get to 3, and that's it. So it's going to be the epsilon closure of the set containing 2 and 3, which is just the set containing 2, and 3. Therefore, we're going to have a transition from 1, 2, 3 to 2, 3 on the character B. All right, so the last sort of state that we have to fill out here on our DFA is the empty set state. Now, what exactly happens on the empty set state? Well, that state corresponds to being in none of the states in the NFA. So if we're on none of the states, that means we can reach none of the states by taking any transitions. So we're simply just going to transition back to the empty state on both characters, right? Because we can't take any transitions from none of the states. Great. So we've now gone through every single state in the DFA and filled out a transition for every single character. And let's see, yeah, no, we did that for this bottom one as well. Great. So we have filled out our entire transition function, and we have now completed all of the steps. So after doing this process, it is the case that this DFA will recognize the same language as this NFA. Okay, great. So are there any possible ways that we can simplify this DFA? Like, are all of these states really necessary? Well, in this case, not all of the states are necessary. And the reason that's the case is because some of the states in this DFA are not reachable from the start state. Now, why can we go ahead and just remove states that are not reachable from the start state? Well, it's because we can't reach them at all, which means that they're going to have no influence whatsoever on our path through the DFA. So if we can't reach a state, we're never going to be on it. So we don't need it in the DFA. So let's go ahead and identify those states. So take a look at this bottom left state here. Notice that there are no incoming arrows into the state from any other state in the DFA, which means it cannot possibly be reachable from the start state. So let's go ahead and get rid of this state here. Great, erase that. And all the transitions associated with it. And then I'll go ahead and draw back in this start arrow here. Great. So we've removed one of our removable states. Now, are there any others? Well, it turns out there is one other removable state, and it's the state 1. And the reason why is because there are no incoming arrows from any other state in the DFA going into 1, which means we cannot possibly reach that state. Therefore, we want to delete the state and all of its associated transitions. Great. Now that we've removed all the removable states, we have our completed DFA. This DFA will recognize the same language as the NFA on the left. Now, just to review the process we went over, I think the easiest way to go about this translation process is to just simply go through the definition of a DFA and make sure that all of the things are met. So remember, when we set up the set of states, we set it to be the power set of the set of states in the NFA. Then when we went to do the start state, we simply took the epsilon closure of the start state in the NFA, and then the set of accept states were all of the states in the DFA where the set inside the state contained an accept state from the NFA. The alphabet was simply the alphabet from the NFA minus the epsilon character, and the transition function was that long process we just went over, but it's simply finding all of the states reachable from a set of states on a particular character, and then taking the epsilon closure. Great, so that is how you translate an NFA into an equivalent DFA. Thanks for watching.